Hey everybody. So who's actually heard of Groq? Notice there's a Q, not a K, so hopefully that doesn't confuse people. Yeah, Groq, we are an inference first provider. How we do that is we build silicon, systems, and the software. So we're essentially building everything from the sand all the way up to the cloud API and provide access to our systems. So why are we doing this? Well, we're living in a world of compute scarcity. So this is a recent quote from OpenAI's Greg Brockman, where he's basically saying we're heading into a world of absolute compute scarcity, where compute is the driver of economic productivity. Compute is the driver of economic productivity. So what's the implication of that? So 20th century, who are the winners and the losers? If you had access to oil, right? Your proximity to oil and access to it. In the 21st century, your access to compute will define if you are a have or have not in the new economy. So this is a very important problem that we're trying to solve, right? And we're responding. Massive compute build out, over $3 trillion of spend in the next few years. So there's this exponential growth in the amount of compute that we're building. So these aren't really data centers anymore, they're compute centers. So these are the things that will provide and drive the new economy. So why am I talking about this at a PyTorch conference? So ultimately, software is the gateway into this compute, right? No one's going to be programming these things at the ISA level. Software, we need the PyTorch abstractions to enable us to move fast, leverage the compute, and build quickly such that we can provide access to everybody. So, and you're seeing this, the industry knows this, right? These high-level frameworks, there's been this explosion of different programming models, libraries, frameworks, you name it. Vendors have a strong incentive to create this diversity in frameworks such that they can influence you, the developer, to use their platform. There's good things and bad things about this. At some point, the diversity can lead to complexity, confusion, and kind of an impedance to fast development. So PyTorch ultimately has become the lingua franca for ML. A little bit of a controversial statement, but I think that's generally true. I think this is something that the PyTorch community should be very proud of. They essentially built something that's flexible, easy to extend, easy to use, easy to understand. So these are all good things, right? We should be very happy that we've hit this point and continue to build on those premises. But there is complexity that's creeping in, right? So if you take a look at the PyTorch ecosystem, there's this really explosion of operators that we're building into the ecosystem. Why is this happening? Why do we need 20 different convolutional operators? They all kind of do the same thing, right? Well, vendors need to do this because of performance. If you actually compile directly from the PyTorch native operators, you get pretty mundane performance on your device. A solution to this is to have vendor-specific implementations of each of these operators to do the same thing. On top of that, you have vendor-specific kernel fusions of these operations. So you're essentially like permuting all these operators, creating different implementations, different possibilities. It does create a bit of an impedance or inertia to move forward. So this is a problem, you could argue. Why is this happening? Well, ultimately, it's very hard to build a compiler. I think we all know that. One of the hardest problems in computer science, some of the smartest people in the world working on this problem, many of whom are in this room. But it is a very difficult problem, right? Ultimately, what a compiler is trying to do is map these algorithms onto the hardware substrate such you can access that scarce compute as efficiently as possible, right? Sounds easy, but very hard to do, right? Your algorithms, especially the algorithms of today, their data flow, very parallel. But your hardware, in some sense, is non-deterministic, right? So what does your compiler have to do? Well, they have to make conservative assumptions to maintain the faithfulness of the programmer's intent onto that hardware. And that leads to poor performance, right? So the instantiation of this problem really comes down to maybe 3 major items. So the memory latency, it's unpredictable, right? You know, all of these spatial processors, they have a very complicated memory hierarchy. And oftentimes you have to fight with that as a software developer and a compiler developer. Thread synchronization, so threads. This is the superpower of today's multi-core processors, right? That's how you get the massive parallelization that you need to run these neural networks. But you have to synchronize them, right? Oftentimes there's massive collectives that occur periodically in the neural network. What does that mean? You have to share data, right? And you have to make sure you're not clobbering yourself with dependencies, memory dependencies, essentially. And then finally, complex interconnect. Again, kind of related in the sense that this comes down to non-predictable data movement that's on the device, right? So how do you get around these things? Well, you can take a couple approaches. You can, just keep on banging your head on these problems, trying to make the compiler better, right? And a lot of people are doing that. You can kind of bypass the problem, which explains that chart that I showed in the previous slide. And these are kernels. So just get a lot of smart mathematicians, physicists, computer scientists, build out a massive kernel library. Thousands of operators that are customized for different types of fusions and different operators. And this is what we're doing as an industry, right? You look at all the job postings for the hyperscalers, big tech companies, kernel engineer. That is something that is in demand. And it's something that we're continuing to build, right? Or you can ignore this problem. Just don't do it, right? So this is one approach that Groq has essentially taken. So instead of having that non-predictable architecture, you can make it 100% transparent to the software and predictable. So Groq has an instantiation of this philosophy where essentially the memory hierarchy, we don't have one. It's a flat memory that's totally controlled by the compiler and the software. There's no virtual address space. The compiler itself assigns every single physical address in your program. The interconnect, very simple. We don't have a 2-dimensional grid. It's purely 1-dimensional. Significantly simplifies the routing problem for the compiler. And then finally, it's single core. We don't really deal with threads. So the thread synchronized problem just basically disappears. So the result of that, building a compiler for an architecture that is deterministic in that fashion, significantly simplifies. So instead of blowing up the number of operators from PyTorch down, we're essentially doing the opposite. So we're effectively taking those thousands of PyTorch ops, canonicalizing them down to tens of operators, right? Fundamentally, that kind of makes sense, right? The types of operators or number of operators you need in your neural net is very, very small, right? And this is exactly what we're doing. From that, then you can do your rewrites, lower it down even further to vector operations that are much more amenable to what we have on our hardware, and then schedule that. So taking a look at the building blocks on our LPU, ultimately this is the core abstraction of what they look like. Ultimately, if you take a look at what's on our LPU, there are these columns of functional units or SIMD units operating on 320 byte vectors. And the data essentially shifts left to right and right to left into those SIMD units. We have 4 types. That's it. Very relatively simple. So we have a matrix execution module, or MXM. Basically does vector matrix operations. We have a SXM, or switching execution module, basically doing reshapes on those vectors, or primroots. Memory, somewhat self-explanatory, just load stores of those vectors. And then a vector execution module, which deals with kind of those non-linear operators that you find in your neural net. And then to create the overall architecture, what do? We just create a linear combination of those core functional units in a 1D fashion, and that's it. That's all we're doing. Again, so this significantly simplifies the problem. Software has 100% access to every single functional unit. And the routing problem is essentially this one-dimensional movement of data, left to right and right to left. So it's a bit of a cartoon depiction of a program that's actually running on our LPU. I think this is a CNN. But yeah, each of those dots is a 320-byte vector. And it's 100% software controlled. So what I mean by that, the compiler is statically scheduling every one of those operations and movement of those dots. Totally transparent to the compiler. So in some ways, some people think, oh, isn't that complicated? It actually makes the compilation process much simpler. And so the result is we're able to actually serve tokens relatively efficiently. I love this chart in the sense that it shows the diversity of providers that are providing access to this precious resource that is compute. And this should continue. You want a lot of vendors providing this access to everybody such that we minimize the number of have-nots in the global economy. And this is an opportunity for PyTorch, right? So instead of having additional complexity, PyTorch should be informing the hardware vendors of what to build. So historically, the process has been the other way around. You start with something like a RISC-V, you vectorize the heck out of it and see if it can run neural networks more efficiently and go from there. Maybe stamp out more multi-core and things like that. But it's kind of a backwards approach, right? RISC-V, a lot of these architectures were built in a world where single-threaded performance was king. It was very different 20, 30 years ago, but this is fundamentally where these architectures were developed from. Today, you have to rethink things. So instead of going from where we were in the silicon world to ML, you should kind of go the other way around. I have my PyTorch application. What do I actually need to build based on the applications of today? And that, I think, is the opportunity for the PyTorch community to help influence and ensure that this compute scarcity problem doesn't stagnate the industry and we can move fast. All right, that's it. Thank you.